But yeah, this isn't something that I just got recently to like make the picture true. We've had him for years. Mr. Gonzalez has had a pet honey badger for a long time. In fact, Ollie went to Rome with us last year. He arrived a couple of days late, but he got there eventually. He went there through by way of Barcelona. He got on the wrong plane at some point. He was in one of our bags. My wife needed a special little slot that was big enough, so he only traveled because she needed something to take up some space to hold all her crap in place. So Ollie made that suitcase. Okay, so size of a char in C is usually the size is usually 8 bits because that's the smallest chunk we can deal with. Actually, ASCII is 7 bits, but 8 bits is our smallest data type in C. In Java and more modern languages, we represent chars as Unicode, so we use it as 16 bits. So now with that in mind, is the size of a char pointer different than the size of an int pointer?
It shouldn't be.
No, a pointer is a pointer, right? A memory address in an operating system is the same. So the question is he actually wearing the mask? Or is that...
I found it when I was cleaning out my drawer earlier.
Oh, no. I'm talking about Eric. You look normal, Luke.
Oh, understandable.
Fantastic. All right. So the size of a memory address is the same. Regardless, our operating system dictates the size of a memory address, right?
Just as a quick question, isn't size of just kind of a standard C thing? So do we even have control over that?
Oh,
or is that just kind of all in GCC's hands?
We really do have control over it because we wrote get mem. So, I mean, what you're saying is what if we use the size of function? I'm saying we probably can't rely on the size of function because that's going to give us the size of a C data type. That's not the same as our data types necessarily, right? We have to imagine our data type. So, you know, right now, what we're processing here is, remember what this class is. This class is the applied side of 350. So this is an operating systems class that we explore through systems programming by writing an operating system. Now, as an operating system implementer, we have decisions that we have to make, and one of those decisions is how big is a memory address in our operating system? What are the things that drive that? What makes us pick a 16-bit memory address versus a 32-bit memory address versus a 64-bit memory address? You know, why might we pick a smaller memory address than a larger one? What's the advantage of a 16-bit memory address than a 32-bit memory address? What's the positive of a 16-bit address over a 32-bit address?
We can fit that in our registers.
Yeah, it's smaller. Kind of like, what's the advantage of one of those smart cars versus a pickup truck? You could fit more than a couple of those smart cars in your garage. You can only fit one pickup truck in your garage. Okay. It's smaller. Now, that smart car might not be big enough for a family of 8. So it still might not be the right tool for the job, but it is smaller. So we have to find what's that sweet spot for us. What are we ultimately trying to do? What's the job of a memory address? When we talk about pointers, what job does the memory address actually solve?
Remembering stuff.
Okay. What stuff specifically? When we think about memory addresses, because actually that's, I joke, but that's not actually, technically, it's not actually correct. Variables are how memory is how we remember stuff. Memory addresses are how we point to where we've remembered things. So a little bit of a caveat, not like a major thing, but you know, a little twist. So I'm still fishing for, as the implementers of this operating system, we're the decision makers. What is, so actually what I'm concerned about here is, it seems like in doing the in writing the assignment, you solved a 300 level type programming assignment without really thinking about why we were solving it. Seems to maybe be the case. So that's okay, we'll swing back through it now. So we are now the operating system implementers. We're having to decide how big should our memory be? How big should our memory addresses be? What problem does a memory address solve? What are the things that we use memory addresses for? I just mentioned, Blaine, that we use a memory address to point to where in memory we've remembered something, right? Okay, so we might point to bucket 0 of memory, bucket 1 of memory, bucket 2 of memory, so on and so forth. So a bigger memory address lets us do what?
Have more buckets.
Store bigger
More
stuff.
buckets. More buckets. It means I can point to more individual spots in memory, right? So if I have an 8-bit memory address, how many buckets in memory can I point to?
8.
255.
Yeah, 256.
Okay.
0 to 255. So with an 8-bit number, my range of values, so think about it, 8 bits. 8 bits can uniquely represent. So again, we're trying to always think about the idea of using bit space to represent things. It's not always magnitude. In this case, it is, but we might think of, if we have 8 zeros and ones, what are the number of unique ways that we can jumble up 8 zeros and ones? The answer is 256, right? There's 256 unique ways that we can represent 8 zeros and ones, 2 to the 8th power. All right. So let me ask you this: is now, and that happens to go in line with magnitude, because I could also use 8 bits to represent the numbers between 0 and 255. It happens to line up with math. Instead of me saying, well, I'm going to use 4 bits to represent this thing, and the next 8 bits to represent this, and the last 16 bits to represent something else. I'm saying if I have a memory address, and if I ask the question, is an 8-bit memory address enough? I say, well, I can know 256 unique things with 8 bits. Is that enough? Is that enough to represent the things in my memory? Well, is it? Is 256 things enough to represent the things in our memory?
Well, it depends on what you need to represent.
Okay, so let's go back and let's think about, well, what is memory? What's this? Yeah. So we want to think about what's the nature of our memory here. Oh, that's not what I want. Just want a new slide. So nature of memory. Our particular operating system here, I think we have 32 megabytes of memory in our box emulator. Does that sound right? I haven't looked at the resource file in a while, but I think we said we have 32 megabytes of RAM in our computer. All right. So how do we use this memory? What kinds of stuff? So this is 32 megabytes of RAM. What do we store in RAM? What things do we put there?
Pretty much anything that has to be used more than once.
Okay, well, we could also put those things in registers, can't we? I mean, can't we load something into AX and use that more than once?
Well, we could.
Okay, So
if you get lucky on no one else needing to use AX.
okay, so our RAM is like overflow space, right? So we have our processor, which has these really, really, really fast buckets of memory on it that we use sparingly. We have to be careful how we use those things, right? Because that's part of the logic of how our CPU works. And we don't have to write that, right? Part of our operating system is we're saying we are writing an operating system that'll run on an i386 processor. That's given information. So a box is emulating an i386 processor for us, and we're saying that's what we have. So that guy has this collection of registers on it that can each hold, 16 or 32 bits of memory, whatever it is, whatever those different registers are. Then we have the high and lows, but it's a very finite, fairly limited number of resources there. So as we write more and more complex programs, we imagine that we're going to need to store bigger things someplace else. We need to have an overflow space, right? If you got a little tiny house and you got a big yard, sometimes you got to throw some stuff out in the yard. That's where you keep the pink flamingos, right? Isn't that, I think it's still a joke. But in any case, that's what RAM is. RAM is the still pretty fast memory that we store things that we want convenient, fast access to, but that is either too big for the processor, for registers, and we haven't talked about cache in between, but let's just keep it simple for us and say we either have registers or we have system memory. That's our world right now, right? Because we don't even have hard drives yet. We don't have file systems. Okay, so we have registers and we have system memory. Registers are only going to be things that we're immediately using. So everything else that we might use soon, even if soon is 3 instructions later, is going to be in system memory. All right. Now, how big are those things?
I have a question real quick.
I thought V's not even here.
Yes.
No.
All right. No, it says
I have a quick question. So then basically you're saying that the register is not stored in RAM, right?
Correct. The register is the physical part of the processor. So if you think of the processor as like a car, the register is like one of the seats in the car that stores a human. It came with the car. It's not something we move around and stuff. We can move things in and out of that seat in the car, but that seat's always there.
Then to continue the car analogy, would RAM be like this trailer that you're towing behind the car?
Yeah, potentially it could be like a big U-Haul thing that you drag with you. It's kind of part of your solution to travel. You need the car, and then you need the bigger storage in the back, something like that. I think that's fair. So things that we might store in RAM might be like a string, right? We've been doing those. We've been working with strings quite a bit. In fact, today's whole homework assignment was about strings. So we want to store a string in memory. Now, if we have a string that is 20 characters long, how much memory does that take?
Would that be 1?
Tell me why 1. And
because
it's 1 what? Is it 1 mile, 1 foot, 1 byte, 1 cat? 1 what?
Because basically what you told me, like back then when I asked the same question. So for example, if we have like a for loop, so memory address would be like the I of the for loop. And then like in that memory address, they store a value, which is like, it doesn't matter how long it is. It's just like memory address is just like the one that points you to that value, which is like the I position in the for loop.
You're talking about it has a single base address.
Oh, my bad.
Well, no. Well, I mean, but you still haven't answered my follow-up question. You said, would it be 1? And my follow-up to that was 1 what? If I asked you if we had a string that was 20 characters long, how much memory would that take? And you answered 1. And then I asked you to clarify what you meant by 1. So it's 1 what? You're talking about the base address. We have to remember where the string begins. And that string begins someplace in memory, which is going to be the size of a char, whatever we decide that is, right? And really, it's going to be the size of a memory address is what the value of that's going to be, because that's how we have to decide we're going to subdivide memory up. But if we're talking about an entire string, and a string has 20 characters in it, what is the total amount of memory we are going to need to store 20 characters? Is it reasonable for us to say that we are going to represent chars in our operating system as 8-bit values? And actually, that's not even an operating system decision. That's actually a programmer decision. I think we're dealing with an old enough hardware here that we should go America first and stick with America's standard code for information interchange. So we only need 8 bits to represent our chars. Fair enough? That's how all the examples from the book are anyway. So we're going to use an 8-bit char. So that means to hold a 20-character string, we're going to need 160 bits, right? 80 bits for a 10-character string, 160 for a 20-character string. So you have 20 characters, each character is 8 bits. Does that make sense? All right, so we might.
Wouldn't we also need another byte for the end of
The
string character?
Termination, yeah. So we might store a string. And then the example would be example 20-character string will take up 21 bytes. That's 20 chars plus string termination. So 21 times 8 is 168. So 168 bits or 21 bytes. That's the amount of memory we'll need inside to hold our 20-character string. Now, what V was talking about is, in order for us, this relates back to what Blaine was mentioning earlier, what we're actually remembering is these 21 bytes. Now, we need a way to get to those 21 bytes in memory, and we do that with a pointer. That's what memory addresses are for. Memory addresses get us to the place in memory where something lives. That make sense? Okay, or where something starts. Now, right now, we've divided up our memory into what? When we wrote our memory manager, I know we're using half the memory for keeping track of what's currently taken, and we're using the other half of memory for actually storing the stuff. How many buckets did we decide we're using? Is each of our buckets 1 byte big? So if we have 32 megabytes of memory, and I think we decided that we'd use the first 1 megabyte as system memory. So we actually had 31 megabytes. So that's times 1,024. That's kilobytes times 1,024. That's bytes. And then we'll divide that by 2. So we have 16,252,928 unique buckets in memory. Does that sound like the way we're dealing with our memory right now? Each bucket is a byte. Okay, so that means that we've made the decision that we need to store, we need to be able to count. This gets to our memory addresses. We need to uniquely represent 16,252,928 unique buckets in memory. That's the number of base addresses that we might have to deal with. Okay? So we need enough bits to represent that guy. How many bits is it going to take to represent 16,252,928? Well, we probably want to deal with the power of 2. So we need to decide what's the power of 2 that's big enough to get us there. Well, is 16 bits enough? How many unique values can 16 bits hold? 65,536.
Hello, 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 hello.
All right, so that is 65,536 greater than or equal to 16,252,928. Nope. All right, well, let's go to the next power of 2, 32 bits. How many unique bite-sized buckets can we do with 32 bits? It's 4.2 billion. Okay, so it's size of int in Java, right? All right, so 4.2 billion. Is 4.2 billion? Is that enough to give us 16,252,928 and then some change, right? So actually, if we make that decision, if we say that we're going to represent our memory addresses as 32 bits, we just decide that, what does that also mean? If we choose 32 bits for our memory addresses, this is assuming we want to be able to access memory 1 byte at a time. Because keep in mind, we could make the decision that the smallest chunk or the smallest block of memory that we want to be able to access, maybe we decide that's actually 16 bytes instead of 1 byte. If that was the case, we would take this number, divide it by 16, and now we're at 1 million buckets. Or if I said, oh, well, maybe it's 32 bytes at a time. Well, now we're at 507,000 buckets. So it's all how you decide you want to represent memory in your operating system. So let me come back to this question here in a second. Representing memory, pros versus cons. 1 byte resolution for memory versus 16 byte resolution for memory. I'm just using those two as our arbitrary. So we're going to say 1 byte is the most granular that we can choose to represent memory. We're going to divide up our 32 megabytes into 1 byte buckets. So you have a 32 megabyte array, and we index it 1 byte at a time. All right, versus the same 32 megabytes subdivided into 16 byte buckets. What's the advantage of 1 byte resolution for memory? Which, by the way, is not how it's typically done, even though we've done it that way.
Well, that would be kind of finer control over memory.
Least wasteful of memory, most granular control. Now, I'm not going to explain this yet until you tell me the other one. If this guy is least wasteful, this guy is more wasteful, right? What does that mean? What does it mean for 16 byte blocks of memory? If that's the smallest chunk of memory that we can index, you know, if the first bucket of memory is at bucket 0, the next one is at bucket 16, and the next one is at bucket 32. It's actually bucket 0, bucket 1, bucket 2, but bucket 1 is memory address 16. It's our second 16 bytes. What does it mean that that's more wasteful? These are going to be terms from 350 that you, go ahead, Blaine.
Well, I was going to say that now if we're going to store a string as individual chars, we're going to have, you know, a single char taking up 16 bytes instead of 1 byte.
Yep.
That's what 16 much times the space.
Well, actually the char will still only take up 1 byte, but the bucket that that char lives in will be 16 bytes.
It's not being used anymore. We can't access further in it.
Yeah, it's like me going swimming in the ocean. So even though I'm big, the ocean is bigger, so I'm only taking up a little tiny little spot of the ocean, right? What's that called? What's that called when we have a place in memory that has a whole bunch of wasted space because we're only using a smaller percentage of the entire stuff available?
Padding?
Who?
Padding? No.
That might be what we do to fill up the space. But what's from an operating system perspective, this would have been something you learned in
it's fragmentation, right?
Fragmentation, specifically what kind of fragmentation?
Memory fragmentation?
So internal fragmentation. You talked about it in terms of internal and external fragmentation, probably when you talked about paging memory management. So internal fragmentation would be wasted space within a bucket. So for your paging memory management, you would have talked about it in terms of you had a frame, and the frame was, in this case, 16 bytes, and you put 1 byte in there, you had 15 bytes of internal fragmentation, wasted space inside of a single bucket of memory that you can't make any smaller. What's external fragmentation? If that's what internal fragmentation is, what's external fragmentation? So the hint would be external to the frame, right? When does that occur? If we have 20 bytes of free memory across all of memory, are we guaranteed to be able to store a 20 byte string? So I have 32 megabytes of memory, and I have 32, I'm sorry, I have 32 megabytes of total memory. It's almost all filled up, but I have 20 bytes free. Am I guaranteed to be able to store a 20 byte string in that space?
Wouldn't it have to be like contiguous then?
Yeah. So this goes back to contiguous memory, right? Memory in a row. So if I have 20 bytes total available throughout memory, it might not be right next to each other. So it would be unusable memory potentially, and that would be external fragmentation, right? Maybe I have 4 bytes of external fragmentation in one little area because it's a space that's not able to be used because I have 20 bytes I need to store. It needs to be stored contiguously, and the biggest spot I can find is 4 bytes. Can't store the string even though I have 20 bytes total available. So that would be external fragmentation. So that's internal fragmentation, would be more wasteful. We have no internal fragmentation with 1 byte resolution, right? If we decide the smallest data type we have is a byte, we either store something in there or we don't. It's either completely packed to the gills or it's empty, one of the two. So we would say this gives us a lot of control, but also has the consequence of us having to have large memory addresses in order to index all of the individual buckets, because each bucket is of size 1 byte. Does that make sense? That's the trade-off of that. Now, it's okay. It's easy. I like using byte.
I have a question.
No questions, V. You ran out a
Why
while.
are you so
No.
Go ahead. All right, what's your
Okay,
question?
I have a question. So for that saying, for example, if I have a string that have like 20 characters, that mean if I'm using like 1 byte resolution for memory, that will be 20 memories total, right?
In a row.
Okay.
20 buckets of memory in a row, each one being 1 byte. Yeah. With tacking on what you said earlier, somewhere there would be a memory address which points to the beginning of that string in memory, wherever bucket 0 is in memory. But in terms of its actual storage place, it would be taking up 20 bytes, 20 1-byte buckets all right next to each other.
So then I have another question. So, using the same thing. So like if I have a string with like 20 characters and now we're using the 16 byte resolution, would that means I need 2 memory address to store that?
Well, okay, so using that as an example, that's a good question. So 20 byte string with 16 byte memory resolution, using that as my example, that means that I need to store 20 characters, but my smallest bucket size in memory is 16 bytes. So that means I'll need to do 20 times 16. So I'll need 320 total bytes of memory. Bytes of memory to hold my 20 byte string with 300 bytes of internal fragmentation, because each bucket will have 15 bytes of internal fragmentation associated with it. is I'll put my 1 byte string at the very beginning of the bucket and then have 15 bytes of open land after that until I filled up that bucket of memory. Then I go to the next bucket of memory. I put my next character for my string, 1 byte, 15 bytes of open land after that until I get to my next bucket of memory. Right? So if I'm using 16-byte memory resolution and I'm storing a 20-byte string, the total amount of real estate that will take is 320 total bytes of memory, of which I've wasted 300 bytes to store my 20 bytes. Does that make some sense? It's kind of like the XML of memory storage, right? XML, we talked about in some of your other classes, XML versus like JSON. XML is very wordy, lots of fluff in there. Your actual data is really tiny, but you have all this text to represent it. So we would call this inefficient, but the question is this bad? Because I can tell you what, this is significantly closer to how it's actually done than the 1 byte resolution. That's the trade-off, especially today. Consider early days of operating systems, it was a much harder decision to make, right? Because early days of the operating systems, memory was really expensive. 300, I mean, this is what? 300 divided by 320, that's 94% waste. If you're wasting 94% of your really, really, really expensive memory, you're not a happy camper.
I have another question. So what that means, I'm using 20 memories total to store 20 bytes?
20 buckets of memory, each bucket being 16 bytes. So any way you cut it, if you're storing a 20-byte string, you will use 20 buckets of memory. The question is what kind of memory resolution are we using? If it's 1 byte resolution, then a 20-byte string will take up 20 bytes of memory. If it's 16-byte resolution, then a 20-byte string will take up 320 bytes of memory. A bucket's a bucket. How big we decide each of those buckets are is determining how much space we have. If you think about, you have your bedroom at home and you're going to go get a bunch of storage containers from Target to organize stuff in your room, and you're literally going to fill up like an entire wall of your room, just buckets stacked on top of each other. If you get the smallest little containers that you can find at Target, you could put a whole lot more of those containers in that wall. But if you get larger containers, you can put far fewer, but you can fit larger things inside of each of those buckets, right? So the idea is that it's the same amount of physical space. That wall has an amount of space associated with it. And you can either have 200 individual buckets to access that, or you can have 20 individual buckets to access that, depending on the size of each bucket. We're shooting for that sweet spot. So a 20-byte string will take up 20 buckets of memory, however big 20 buckets of memory is. And that comes down to our memory resolution.
So you said that this is far closer to what is actually done. But in my experience, at least on the Raspberry Pi, a single memory address refers to a 32-bit value.
Yeah, 4 bytes.
So, right, a 4-byte value, which is far closer to 1 than it is to 16.
Well, yeah, what I was referencing is that the idea of having things bigger than 1 byte is more common. Yeah, I used a big number here to really show us how inefficient this is. So yeah, you're right. So modernly, if I just copy this, if you want to see what the real decision is, 4 bytes is usually a bucket size in memory. So we're going to have, so it'll take 80 bytes to store 20 bytes. So that'll be 80 total bytes to store our 20 bytes, leaving us with 60 bytes of internal fragmentation. 60 divided by 80, so that's 75% wasteful. That's our modern approach to this. Now, usually we would say 75% wasteful doesn't sound so great. But today, that's not that big a deal because memory's cheap. I mean, we got to really abuse our systems to run out of memory in our system, right? Today, unless well, that's a true statement anyway. You cut it, because it's so cheap just to add more RAM. All right, so this is indicative of what it looks like today that we decide to kind of meet.
The other question then.
Yep.
Does this relate to kind of the 32 versus 64-bit operating system? Is kind of what size of value are they expecting to be able to store in an address?
It can, but it doesn't necessarily have to. The phrase of 32-bit operating systems versus 64-bit operating systems are used a little bit loosely. I would say maybe officially, if it's a 32-bit operating system, then everything in it should be 32-bit systems. So memory addressing would be 32 bits. The CPU management would be at 32 bits. File systems would be 32-bit file systems. So you'd see a whole bunch of maximums that would be very related to each other, but that's not necessarily always the case. We really saw it in some of the early days of the transition between 32-bit and 64-bit, actually no, 16-bit and 32-bit operating systems, from like Windows, early Windows 95 to later Windows, let's call it Windows 98. What you had is you would have a situation where like the largest hard drive partition you could have was 2.1 gigabytes, which was based off of a 16-bit file system. Yet you could have more RAM that was based off of a 32-bit memory subsystem. So they didn't always match up, but it certainly gives you a clue into at least what neighborhood you're working with. I think we saw it again in Windows Vista days, where you could have huge multi-terabyte hard drive partitions, but the maximum amount of addressable memory was 8 gigabytes, right? And your next jump up from 8 gigabytes is 2 terabytes. Well, that's a pretty big jump. Well, it's because you went up to the next power of 2. So it's that was a decision that, so at that, and that affected people, because at that point in time, there were people who did have machines with 16 gigabytes of RAM, and they would install the 32-bit version of Vista on it and be able to see their entire hard drive, but only be able to see half their RAM because it couldn't address all of their RAM. I don't know if any of you remember or had that happen to you, if you had a machine or knew of somebody who had a machine at that point in time. But we've seen some of those things in the transition before. All right, so these are decisions that the operating system person needs to make. We're gonna stick with 1 byte because 1 byte makes.
I have a question.
Go.
Please.
All right.
So then, for example, let's say if I have an integer that have like 4 bytes to store, would that mean I only need 1 memory address then?
Well, okay, are we going with our 1 byte resolution?
No, if we like back to your example for like 4 byte memory resolution.
1
so
bucket.
let's say that's only need 1 bucket, right?
Well, you always store a value in 1 bucket. The question is whether or not it completely fills up that bucket or not. If a value is bigger than your buckets, then you need to look at how do I bridge more than 1 bucket to store stuff. So in your example there, if we're using 4 byte memory resolution, an integer would fit in the 4 bytes fully with 0 internal fragmentation. Whereas a char would only use up 8 of those bytes, leaving you with 24 bytes of internal fragmentation for a char. You'd have 24 unused bytes because you only stored 1 byte in there, or 24 unused bits, 3 bytes. So an int fully fills it up with all 4 bytes. A char only fills up 1 of the 4 bytes, leaving 3 bytes of wasted space. Does that make sense?
Yeah, so then for example, let's say like back to your like assumption too, like if I have something that more than 64 bytes, and you said I need to find a way. So what would be the way that you're saying then?
Well,
Like,
let's
how's that work?
you had a 64 byte integer, you would store half the integer in one bucket of memory, the other half in the other bucket of memory, and then you'd have to know that, oh, when I go in, I process load, you know, this giant number, this long, for instance, I need to grab from 2 different bytes of memory, bring them into 2 different 32-bit registers, and then treat those 2 registers together as the full magnitude of the value. Because you don't have enough space, right? If you have a comic book collection and you have 2 trunks and all the comic books won't fit in one of the trunks, you got to split the collection into 2, put it half in one trunk, half in the other trunk, but you still have one giant comic book collection. You just divided it into 2 different buckets. So then when you want to go and show somebody your comic book collection all at once, you want to have the whole value of your comic book collection, you'd have to bring them out of both buckets to give you the collection together. So all these things are just how numbers work, right? We're just deciding how big is the bucket and what are we allowed to put in that bucket. All right, so we are going to stick with, for simplicity's sake, 1 byte resolution for memory. So we won't have internal fragmentation in our world. So this is going to have 2 things going on with it. Chars will conveniently store, but ints start off being inconvenient. We actually need 4 buckets of memory to store 1 int. Does that make sense? And then we have to decide, do we store it in little endian or big endian? Where's the most significant bit of it? But we'll deal with that later when we start dealing with numbers with file systems. All right, but this is how our memory model is ultimately going to work. We're going to decide that every 1 byte of memory, well, my memory is divided into 1 byte tiny buckets. So coming back over here, if I need to store a memory address, well, actually it's over here with my 32 megabytes of memory, we decided that for 32 megabytes, how many bytes is that? That's 32 times 1024 kilobytes times 1024 bytes. Now we're only using half of that, and actually it was off of 31, right? So we're only using half of that amount of memory because we use the first half of our memory for marking whether it's available or not available, the second half for the actual storing stuff. So we'll divide that by 2. So here's our 16,252,928 total buckets in memory for my 32. I need a big enough number to represent that. We decided that we could. I'll keep it on this.
I have a question. Are we not using our memory for stack at all?
Well,
Because I know what you told me was that we have, because the memory start at 2 and then end at 31.9 in megabyte, because you said that the little pieces for
yeah, that's fine.
the first 2.
No? And we are. It's unrelated to this discussion. I mean, you're not wrong. We are. So we're not quite. This number isn't 100% accurate because it's actually like 30.95 or something like that is my percent of memory I'm actually dealing with, because I am storing some memory at the end for my stack size. But anyway, you cut it, we're going to have a bigger number than this for our memory address. We're just using this number, so we can call this number the ish number. This is how many ish buckets of memory we need to be able to index. We need to be able to count that high. How many buckets in terms of a power of 2 number of buckets must I get to in order to count that high? Well, 16 bits isn't enough. That only lets me count to 65,535, less than that. 32 is enough. That lets me count to 4 billion. Bigger than that, way bigger than that. All right, so we're okay with that. We didn't have to deal with the exact size of this, taking away the stack part of it, because we jumped from 65,000 all the way up to 4 billion. So we leapfrogged this guy by a ton. So we have plenty of room then. And that's where this question comes in. If we choose 32 bits for our memory addresses, assuming we want to be able to access one memory byte at a time, what does that mean for our maximum size of memory? So what is the maximum size of memory that we can address with 32 megabytes, or 32 byte memory addresses if we're going to have a memory resolution of 1 byte? Well, 2 to the 32nd is my 4 point blah blah billion, right? So that's the number of 1 byte buckets I can address. So if I divide that by 1024, that gets me kilobytes. So I divide that by 1024, that gets me megabytes. So that means a 32 bit memory address will allow us to have 4,096 megabytes, or 4 gigabytes of addressable memory. So there's my 4. So that means that even though our machine, our fake machine here, only has 32 megabytes of RAM, by choosing a 32-bit memory address, which is overkill, right? It's overkill for this problem because we're saying, hey, I want to have 1 byte resolution. Done. But because of that, we now can support up to 4 gigabytes of memory with our 32-bit memory addresses. That means without changing our operating system, we can support hardware up to 4 gigabytes of RAM, which is substantially bigger than 32 megabytes of RAM. Does that make sense? Whereas if I used a 16-bit memory address, I could not have represented the 32 megabytes of memory. It wasn't big enough. All right, so this gives me some wiggle room to grow into. So max RAM supported at 1 byte memory resolution is 4 gigabytes. That makes sense? How all that stuff is working together? We have to know what our resolution is. And in this case, we're just choosing, hey, a byte's a byte, and every bucket's going to hold a byte. That then dictates how big our memory addresses are going to be. So we're going to say that in our operating system here, when we go and get enough memory to, when we ask for enough memory to hold this many bytes, it's going to return for us the base address of that. And it's going to give it to us as a 32-bit address in our world. Okay, because a char pointer is going to be a 32-bit address. And we don't have a way of showing it there, but I can show it. Here, let me. This just happens to coincide with, well, I actually already have the exact correct thing. So GCC test.c./a.out. So this is a hexadecimal number, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is that all the values? So I have 12, and each of those is 4 bits, right? Each hextet takes up 4 bits. So that's a 48-bit memory address that it returned there in Linux. And what does that tell us? So, you know, we know the reason the way I got 48 out of this is a hexadecimal memory address. Each one of these is called a hextet, and we can represent the entire hexadecimal language in 4 bits. 0 to 15 can be represented in 4 bits. So this is 12 of those hextets times 4 bits, which was 48. So that means if I have a 48-bit memory address, that is 2 to the 48th power. It's that much memory divided by 1024, which would, that's bytes, that's mega, yeah, that's kilobytes, that's megabytes, that's gigabytes, that's terabytes. So that'll support 256 terabytes of memory in this system, which makes sense. That's a server-based operating system, Linux. So
2, 3, 4, 5, 6, 7, 8, 9, 10, 12.
we only had 8
Who's
of those.
boiling?
What's
Who's
up?
boiling tea in the background?
It's Mr. Gonzalez. He's cooking an animal over here.
Oh, understandable.
Did he send a friend over to my house? Because my camera isn't working correctly.
Did who send a friend over to your house?
I don't know, but my camera's been replaced with this like being.
Oh, that's you?
Yeah.
I thought that was Luke. It looks
I don't
like
see a difference.
Yeah, I don't see a difference.
Boy.
All right. So does this kind of make sense? How this these decisions as the operating system implementer goes deliver us pros and cons. We either are more wasteful of memory at the cost of having very granular control. I'm sorry, we're more wasteful of memory at the cost of having more total memory, expecting that the stuff we're going to store in memory is on average bigger than 1 byte, which is probably true, right? I mean, chars are only 1 byte in C, but realistically, if we look at Java, the smallest thing we ever store in Java is 16 bytes, or 16 bits, 2 bytes. A char in Java is 16 bits. So whenever we store a char in Java, whoa, Linda. So whenever we store a char in Java, we're using 2 bytes. So right off the bat, we're going to have to hack it to work with Java size chars with our thing here. So this is the decision that the operating system implementer has to go through when they sit there and they ponder, what should I make my memory addresses so that it is supportive of the amount of memory I perceive my end user is going to use. What kinds of things are they going to be storing, and how much memory are they likely to want to be able to support? All right. So we're going to just arbitrarily choose to use a 48 or a 32-bit memory address, even though we know we only need to hand out numbers representative of what, 16 megabytes. So we're not going to come anywhere close to using up the whole 32 bits. We just know that 16 bits wasn't enough. We could choose a smaller number of bits, but we typically want things to be powers of 2. It allows us to do things with like bit chips and things like that that are convenient. All right. So in our world here, we're going to presume that this value that comes out of here is a 32-bit value. Even though, I mean, it doesn't matter what it actually is. We're not having to do it. We just know that this guy's going to come out as a 32-bit value. What's that sound?
It's V.
Oh, it's V eating cookies or something?
Ish.
So it's you know, we're going to get a 32-bit memory address out of this guy, but we're not going to use anywhere near 32 bits of it because we're only representing 32 megabytes of total memory. So we only need so what was that, 16 million something or other. So what's that, 2 to the let's go 20th, 23rd, 24th. So roughly a 24-bit value. In fact, I think it's pretty close to exactly a 24-bit value. So if we wanted to actually represent our exact amount of memory, you could do it with 24 bits. But not a power of 2, so we'll just jump to 32. So we give ourselves some ability to upgrade our computer a little bit. All right, so getmem is already doing that. It's going to give us the base address of where this char is going to live, and we're assuming it's 1 byte at a time. So we'll go ahead and store this. This was just our check thing here. All right, so this is going to be the beginning of that memory address. And let's go look at getmem here. Takes in a number of bytes. It goes and figures out some stuff, and it's going to return as a char pointer, a base address where that was in memory. All right, so that's going to be our base address. And let me go back. Ooh, what, string.c? All right, so this will be the base address of, now right now we're asking for char pointers, which means that the thing that knows that knows each of these guys is that knows how to live in each of those buckets is 8 bits, right? A byte, because our memory is divided up into 8 bytes, or 8 bits rather. So if I draw the picture, what I just got there is this. This is bucket 0, bucket 1, bucket 2. And I'll just pick something out in the middle of nowhere. So this is 32, 40, 48. So this is our memory addresses. These are our indexes. So it just so happened that our base address was at address 32. So bucket 0 was an offset of 0 from base address 32. 8 bytes later, or 8 bits later, sorry, is bucket 40. 8 bits later is bucket 48. All right, or if we want to think about these guys as byte size, this would be 33, and this would be 34. Byte 32, byte 33, byte 34. But I think it reads a little better representing them in terms of bits, just so you can see that bit 32 through 39 lives in here. That's a byte. Bit 40 through 47 lives in here. That's a byte. Bit 48 through 56 or 55 lives in here. All right, that makes some sense? All right, so each guy here, though, is only 1 byte big. What kinds of things fit in 1 byte? Well, things that fit in 1 byte are chars. So I could put a thing like A or B or C in here. But that's not what I actually want. What I actually want by my example here is like A, by, and cat. So I want to have this guy point to here. This guy point the base address here. All right, so A, by, and cat. That's
I
what.
have a question.
Yep.
So then, okay, so A is like only 1 byte, but then B and Y is like 2 byte. And now if you only give us like a bucket 40, I mean like 40, it's not gonna hold, no, it's not gonna hold Y though, because it's like 8 and 8, that's 16 total. So would that be 48 also go over to
Well, I'm
Y?
about to ask the question that you're trying to ask,
Oh,
but that's
sorry.
okay. So the question is this guy is a pointer, right? This guy is a pointer. This guy is a pointer. How big did we decide pointers are?
Bytes.
$32 bits. We decided we needed our pointers, we needed to have 32-bit memory addresses. 4 bytes. That make sense? That's what we decided that we needed. So that means that this guy right here, this value that lives here is actually 32 bits. Well, I should say it's supposed to be 32 bits. Supposed to be 32 bits. Supposed to be 32 bits. But we're going to have a real tough time fitting 32 bits into bucket 32 through 39, which only has 8 bits. Does that make sense? We gave ourselves enough memory to hold 4 chars. But I actually need enough memory to hold 16 chars, because my memory addresses each are 4 times the size of a char. These are 4-byte memory addresses. So if this pointer right here, a pointer is a memory address, which points to a place in memory where we're actually storing a value. This is a 1 char in contiguous memory. This is 2 chars in contiguous memory. This is 3 chars in contiguous memory. Does that make sense? That's how these strings are stored. A string is a string is a string. Here's a string, here's a string, here's a string. Strings are always in contiguous memory. If we have a 1-character string, it takes up 1 byte, well, really 2 bytes of contiguous memory with our \0, but roll with me here. In fact, here, actually, if you just so we're accurately representing it. Let's freeze this guy off here a little bit. All right, so here's our 3 separate strings that live in memory. Make sense? 3 separate strings that live in memory. Each of the, so this first string takes up 2 bytes. This takes up 3 bytes. This takes up 4 bytes of memory. They're not next to each other in memory necessarily. They're, in fact, they would, none of them would be, because they're all bigger than 1 byte. So this guy needed enough memory to hold that many characters in a row. 2 characters in a row, 3 characters in a row, 4 characters in a row. So each of these, the way we get to them, this is like a house. This is like a house. This is like a house. Houses have addresses. The size of addresses in our operating system, we've decided, are 32 bits or 4 bytes. That make sense? When we asked getMem to give us memory, we asked it to give us num tokens plus 1 amount of memory. So we asked this to give us 4 chunks of memory. Well, what it gave is it gave us 4 bytes. So actually what we have here is a 4th one on this. So if we're just completely being accurate. So it gave us 4 bytes of memory. Each of these is 8 bits, is what it's actually given us. So I barely have enough memory space here to hold the address for my very first string. I have 4 bytes of memory to hold the address of my first string. 32 bits is our memory addresses. That's what we've decided, right? So this line of code right here, get mem, isn't enough. We need this times 4. So number of tokens do something funny here. So get mem.
You have a 0 on line 51.
Oh, thank you. Number of tokens plus 1 times 4. So this will get us enough memory. Let's put it on the line before it. Get enough memory to hold number of tokens. And actually, we don't need the plus 1 here, because we're not actually holding that. Oh, actually, we do need the plus 1 for a number of tokens, because we counted the spaces, and there'll be 1 more token than that number of spaces. So get enough memory to hold the whole number of tokens, 32-bit memory addresses. So I want to hold 3, by our example, 4-byte memory addresses, which will take 12 bytes. That's why I'm multiplying by 4. 4 is the size of a memory address. 4 is the size of mem address. We chose this. All right, that makes sense? So S is going to hold the base address of where this guy lives. Go ahead.
So hopping back to the plus 1, we added 1 to number of tokens in 52, line 52. So what's the new plus 1 for? Do we also have a separate main character?
Oh, yeah, you're right. The so this plus 1 was, we were putting it in there for the \0. So we don't need it here since we added it up there. Because we're not storing a string at this place. We're storing 3 memory addresses. So we don't need the extra bucket for our \0. All right. So really, even though I'm storing this inside of a char pointer, the only reason I'm doing that is because getMem returns a char pointer. So I'm working with the tool that we wrote. We wrote a function called getMem that gives us that blocks off some chunk of memory somewhere. How much memory? However much I ask for it. I have to give it a number of bytes. How many bytes do I want? Well, I want 12 bytes of memory. That's how much memory I'm going to need to hold my 3 memory addresses. And then he's going to spit out a char pointer, which is going to tell us where that guy begins in memory. Okay? I know that I need to store 4 bytes of stuff at each hop through there. So I'm storing memory addresses. Go ahead.
So is there a reason why don't we just include in getMem, multiply by 4 then if it's always going to return a memory address, right? We know that we want it to be that size already.
Yeah, you're not wrong. Yeah, you're not wrong at all. So, and we could do that. If you want to go and we can update getMem to return 4 times the size of that. Let me actually think about this. We want it to match up to how like malloc works in C probably. We tell malloc in C the number of bytes. Yeah, see, realistically, what we would do is we would have this guy return he's returning a char pointer, which is the correct size of memory, because a char pointer is going to be 32 bits. Let me look at memory here real quick. Yeah, so we're doing it off the base address. And we're returning the bucket number that it starts at. What you're saying is correct if we were implementing a modern approach where we used 4-byte blocks in memory, which frankly would actually make our life a little easier here. But let's stick with the 1 byte. I think it'll be more fun. So we wouldn't multiply by 4 here, because what we're asking for, what getMem does, is it returns us the bucket where 4 bytes begins. That's what he returns. The bucket where num bytes begins. We have to externally know that the size of those memory addresses, if we're expecting it to hold memory address, we have to ask ourselves, what lives here? You know, what lives at this memory address? It's going to give me this base address, and that base address, if it only holds a char, is only going to be 1 byte. If it holds an int, it's going to be 4 bytes. If it holds a long, it's going to be 8 bytes. If it holds a memory address, it's going to be 4 bytes, because we've chosen 32 bits to be our size of memory address. Right? So this guy doesn't know what kind of value we're going to store at that base address. It's just going to give us the base address, and because we index memory as 1 byte size, this is the bucket number that it's going to give us, that char pointer. Does that make some sense? Let's see, where's my string thing here? Okay, so we have a number of tokens. We know that number of tokens here means that I need to hold this many strings, right? This is how many strings I'm going to have to hold. And how do we represent strings? We represent strings through pointers to the base of that string. So that means I need to hold 3 memory addresses. So actually, I can go back here with this guy. Let's update our picture. Scoot this guy over a little bit. Six, 64, 72, 80, 88, 96, 104, 112, 120, 4, 5, 6, 7, 8, 9, 10, and 11. So we're going to get 12 buckets from this guy. 12 1-byte buckets to be able to store 3 32-bit memory addresses. So I'll put some dividers in here. All right. So the number stored in here is the base address to this first string. So I'm actually going to point to it like this right now. The number based in here is the address for that string. And the number right here is the address for this string. Okay, so this is where we decide from a computer architecture perspective, over this computer organization perspective, how do we treat these values? We have 4 bytes here to represent our memory address. Is our memory address represented, is this is this the ones place over here? And the 2s and the 4s and the 8s and the 16s all the way up to the 128th place? And then is this the 256 through the 4096 place, so on and so forth? Or do we do it in reverse? So is this bucket, is this bit 0 through 7 and bit 8 through 15 and then bit 16 through 24 and then 23, then 24 through 32? That's probably how we would do it. So this is a 32-bit number split across 4 8-bit buckets. This is a 32-bit number split across 4 8-bit buckets. This is a 32-bit number split across 4 8-bit buckets. That makes sense? And because these guys are pointers, these are memory addresses which point to a string somewhere in memory, this 32-bit address tells us where in memory, what bucket of memory we can find this string in. Now, we happen to know that since we only have 32 megabytes of memory, the most we're ever going to have filled, even if we go way out into memory, is 24 of these 32 bits. So worst case is we're going to have 8. This whole last one is always going to be zeros. It's always going to be padded with zeros out here. Whereas we might use what's in these guys here. But chances are, since we're always searching through our memory early on, we're probably only going to be using what's in this bucket here, and never quite getting far enough into memory to start spilling into these other ones. Does that make sense? So this goes back to data representation. We are choosing how to store stuff in memory. I asked for 12 individual buckets of memory from my getNem because I needed to store 3 memory addresses, and each memory address requires a maximum of 4 buckets of memory because we chose to have 32-bit or 4-byte memory addresses. So I can go build this string up. I could say, okay, I need enough memory to build for me a string with 1 character. So I need 2 bytes of memory for this guy, right? So he's going to live somewhere in memory. So here, let me draw this picture. Then I think I have a pretty good idea where everybody's sitting now. Is it fair to say that nobody really thought about this assignment through this perspective?
Yeah.
Let me be the first to say what. But it's okay, because we're also kind of working with C for the first-ish time, let's say.
I tried.
But this is good. Is at least what we're talking about today, is it starting to make some sense how these decisions at the operating system level make sense, are things that we choose? And we get to decide how we represent stuff in memory? Or am I adding some context to this now?
It's starting to make a bit more sense. I think I need to see a bit more application before I can really get it, but.
Okay, so hopefully I pull it together here with these examples then. All right, so we're going to be creating this string. We're going to be creating this string. And we're going to be creating this string. Okay. So just for a moment, let's just forget about these pointers. All right. So we just want to think about these guys in terms of themselves. We're going to ask get mem for enough memory to hold 2 bytes. Correct? All right. So we'll just make this guy red. And then let's say I'm just going to arbitrarily pick these numbers just so they're different enough that we see the examples. So we're going to say this is byte 45 and byte 46 in memory. And this is going to be byte 111. One 12, 113. I'm just arbitrarily pretending like I'm get mem, and I'm assigning memory for where these strings will live. And then this guy will be at 491, 492, 493, and 494. All right, so this is the result of me calling get mem. So if I just I just write the code in here. So if I say get mem, and I pass it a 2, give me memory for 2 bytes, it's going to give me the char pointer that is 45. We'll just say 45. That's going to equal to 45. That is the base address where I can find my 2 bytes. Similarly, this guy is asking for 3 bytes. And actually, let me, oh no, we're good. I had already put my backslash zeros in here. And it just happened to give me a 111. And then this guy is asking for 4 bytes. And we're going to get a 491 from that. Okay, so does this make sense? If I ask my get mem to give me enough memory to hold 2 bytes in contiguous memory for my string, it gives me 45. It just picked me a place in memory where it had enough space in a row to hold 2 bytes. We just are assuming there was already some other crap in memory, so that's why I had to get so far into memory. Actually, these numbers are probably low because we're using the first 1,024 bytes for other things, but whatever. These are the numbers. All right, so this makes sense in and of itself. That's a string that has a base address of 45. This is a string with a base address of 111. This is a string with a base address of 491. Since we say that this guy points to this place in memory, he holds the 32-bit value of 45. So this is going to be, these are 8 bits. So there's my 8 bits. 45. Now let me just Google it real quick. 45 decimal to byte. Oh, yeah, we're good. So that means All right, so this 45 will get stored in these 4 buckets as a memory address, where it'll be 000000000 blah 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 00101101. That's the 32-bit number that represents 45, which is where this string lives. 111. Is this guy? And then 491. Ooh, this is going to bleed into our next bucket. Perfect example. So we got one, that one. Okay. So, since we know that this guy is the memory address where a string lives, we know that this will be 4 bytes big. So we're going to have to go through and look at the values. We have to effectively get the 32 bits of values from those 4 buckets and convert it to decimal to give us a 45. If we want to think about this in terms of decimal, because really bucket 45 is really going to be a 32-bit binary number, which is this guy. So I'm only converting it to decimal because human beings find that helpful. Okay, so that'll help us count. All right, so this 32-bit number, which is a bunch of 0, 0, 0, 0, 0, 0, 0, followed by these couple of bits, turns into the decimal number 45, which happens to be the base address of where this string is. So we will get memory and put this string in memory and then store in buckets 0 through 3 of our memory that was returned from our getMem for the number of things we needed to store, number of strings we needed to store, the base address of that. Similarly, this guy is the base, holds the base address of this 3-character string, which happens to live at memory address 111. So I'm going to ask getMem to get me 3 bytes of memory for this guy, and he returned 111. I asked getMem to give me 2 bytes of memory for this guy, and he returned a 45. I asked getMem to give me 4 bytes for this guy, and he gave me a 491. But now if I want to be able to get to those, if I want string toke to ultimately return an array of strings, this is what string toke is going to return. It's going to return a 12 bucket, in our current example, it's going to return a 12 bucket array of bytes where each grouping of 4 bytes is the 32-bit memory address of where that string lives. That makes sense? So we ask getMem for this much memory. It's all zeroed out with zeros throughout. We probably want to zero it to be sure, especially since in this case, you know, remember before we said, oh, well, if we're asking for some memory, we're just going to overwrite it anyway. So do we really need to zero it out? The answer is probably, because let's assume that this guy still had some values in it from before. from some other previous use of that memory. So now we just went from this guy supposed to represent 45 to representing something much larger. Does that make sense? So when we first get this array coming out of there, we probably want to zero it out to make sure that it's filled up with a bunch of zeros. All right, so initially this guy will be just a bunch of zeros across the board. Then we want to go start filling it up with our token. So we'll have to find out how big is this first token. And this first token, so remember, I'm just going to put in from our application here. Where's my example here? Perfect. Almost perfect. Nailed it. All right, so if I was calling string toke on this guy, the first thing it did is it found out how many tokens do I have. I have 1, 2, 3. So give me enough memory to hold 3 addresses, which will point to those strings. Then I need to go through and collect my first token. Well, I need to first ask, how long is this first token? So 1, and then I hit that space. All right, so I know this first token is going to be a string that is 1 character long plus the 0 for the \0. So then I ask getMem for 2 bytes. And I go through and I fill it up with the A and then terminate my string with the \0. So now I'm sitting right here at the beginning of my next token. So now I need to say, well, how big is my next token? Well, I got to go through twice, right? I'm going to say it's 1, 2, 2 characters long plus 1 is for the \0, it's 3. I need to ask getMem for enough memory for 3 of these guys. It comes back with the 111, great. So now I go back in here. I get the B, I put it at memory address 111. I get the Y, I put it at memory address 112. And then I've hit the end of it. So now I put in a \0 at memory address 113. Next, I'm at my cat. So cat, I will say, how many characters long is this? This is going to be 1, 2, 3. Then I hit the end of the string. So it's 3 characters long. I need to add in 1 for my \0. So I asked for 4 bytes of memory. So I get 4 bytes of memory. It happens to return 491. So now I go through and I say, put the C at memory address 491, put the A at memory address 492, put the T at memory address 493, and then terminate the string. So that's how I go from asking for this, getting myself 3 strings, and filling those strings up with stuff. So going from this to these 3 strings was easy enough. But my last step is I need to turn this number, 45, into its 32-bit binary representation and store them 8 bits at a time inside of this. That makes sense? So at the end of the day, this guy up here that I'm asking getMem 12, and he gave me a 32 in my example here. This is going to be my array of strings. So we want to see this in Java. This is a string array. Or in C, this is a char pointer. is what this guy ultimately represents. A string array is a collection of memory addresses which point to a string. Here's memory address 0 that points to this string. Here's memory address 1 that points to this string. Here's memory address 2, which points to this string. So the kind of animal that will come out of get mem12, this base address that it's giving us, this is something that is one of these guys. We can think of it like an array of strings. He's actually an array of memory addresses. So if you really wanted to just say this is an array of memory addresses that we happen to be using to represent strings right now, but it could be a memory, any memory addresses. So this could be an array of array of int pointers, an array of float pointers, an array of double pointers. So anything that's a memory address will take up 4 bytes in our memory because we've dictated that it will. Does that make sense? All right, so questions about all of this stuff that now puts it in context with how we want to tokenize our string and actually store it in memory in a way that's realistic to how operating systems work.
I have a question.
Yep.
So then the string toke will not we're not printing out a string, but it's printing out like memory address, right?
Well, only if you print it. Yeah, if you were to go through and print out the result of string toke, this is the result of string toke. So if you were to look at the byte, at byte 0, bucket 0 of what string toke returns, it's going to be the number 0. Bucket 1 is the number 0. Bucket 2 is the number 0. Bucket 3 is the number 45. Now, you might be tempted to say, oh, so I just need to look at the last bucket. Well, that's not necessarily true because we see in our last example here that we technically can use all 4 of these buckets for our memory addresses. It's luck of the draw for what we get, right? Because this last one, because the base address of this string started at 491, we have a 0, then a 1, and then a 4. Well, actually, this is a, what, 238? Well, whatever. It's something less than 255 is what that is. We can figure it out real quick, but whatever. So you have to go and put these 4 bytes together to give yourself a final number because that's where in system memory you need to go to find your string. This memory address, all these bytes concatenated together will give you the number 45, which is where in memory you need to go to find your first token. These guys will get concatenated together to give you a 111, which is where in system memory you have to go to find your buy, your next token. This guy, when concatenated together, will give you a 491, which is where you need to go in system memory to get your cat, which is your last token. That make sense? So this is how our memory is going to work because we've chosen to use a memory resolution of 1 byte. A memory resolution of 1 byte with a size of memory address of 4 bytes means that it's going to take 4 buckets of memory to know how to get to one place, one other place in memory. Because we need to support at least 32 megabytes of memory because that's how much our computer has. It just so happens that we actually support up to 4 gigabytes of memory. All right, so I'll grade whatever you turned in for today through the lens of you wrote it as a, I don't know, just a string program. Something like that that doesn't necessarily take the operating system stuff into consideration. So for your next assignment, we'll just keep it the same, but implement a version of string tokenizer that works like this. So string tokenizer should return for you a base address that you can expect will have 4 byte chunks that point to where the different strings are in memory. And then you should be able to prove it by writing them out to your frame buffer and seeing that the strings are what they were supposed to be from that tokenizer. All right, remember, any class that starts after 4 p.m. on Wednesday, it does not meet because our Easter break starts Thursday. So we are off Thursday, Friday. We're also off on Monday. That's Monday. I will be around. So if any of you are working on this assignment or want to ask for help or something during our normal class time or something on Monday or whatever, I'm around anyway. So I'm happy to help. But officially, we don't meet next week. So this assignment will be due 2 weeks from today. That sound good? Questions, comments, concerns, bribes? One thing I did point out, I wrote it on Slack a couple different places. For those of you who are still in the area and you're interested in doing some VR stuff, either now or as we even into the summer, because I think we're going to probably be cooped up for a while. The university does have, I think we have maybe 10 Oculus Go's and several Rift S's and things like that I'm willing to lend out for to people who are. One thing I want to do is maybe do some research around, you know, taking real world, turning it into a virtual world for productivity and, you know, get rid of cabin fever type thing. So not so much, I mean, you can play video games on them, but I'm not so much talking about, hey, let's get together and play video games. I'm saying, let's get together and look at things that we can do in virtual reality that mimic what you might do normally in real life. You know, getting together, playing board games or watching TV shows or something like that, and seeing how that translates into being in a virtual world, talking to each other and things like that, as opposed to Zoom or something like that. So it's something that, you know, because students typically, you know, we don't have a high percentage who have VR headsets, we wouldn't really have the ability to really test this. But if you are in the area and want to borrow either a Go or one of the higher powered ones, you would need a good gaming machine for those. I'm happy to do that as long as you're willing to participate in some of that stuff. So just send me a private message on Slack and we can arrange for the pickup or whatever. I suppose if you were like super interested, we could, I haven't even thought about it, but we could think about shipping one. It might cost more to ship it than to just buy one. but in any case, you might, they come down in price so much. The Oculus Go's are under $100 you can get them for, certainly used ones. Yeah, so in any case, keep that in mind if you're interested. All right, I will.
Also,
Yep,
I put a link in Zoom chat. There's an app called Spaces. It's supposed to be like this. You can do like Zoom and Skype and whatever, all these things in VR, similar to how VR chat works. Something to try out.
Sure. Yeah, so I mean, I think those are the kinds of things that I'm interested in messing with, is kind of productivity tools in VR in case this is the new normal. You know, if we're gonna all become bubble boys or bubble girl and have to go outside only wearing, you know, hazmat suits, and we really can't be in real places ever again. I don't think that's going to be the case, but you never know. You know, how can we leverage technology to not have to deviate from normal life too much? All right, well, I will see you when I see you.